Washington State University. Go Cougs!
Hello everyone. In this video, we're going to cover Lesson 5 of the Activity Change Detection module. In this lesson, we're going to outline the Physical Activity Change Detection framework. Let's begin. In the previous lessons, we learned how to download time series activity data from the Fitbit API and how to create activity density maps in order to visualize the data. For example, if we download 21 days of Fitbit data, we can plot the minute-by-minute steps data using an ADM, such as this one. If we were to perform exploratory data analysis of this 21-day Fitbit dataset, we could do so initially by looking at one of these ADMs. We can tell a lot about this particular individual's lifestyle just by looking at this ADM. For example, the first day of the week is a Thursday. If we compare Thursdays to Thursdays to Thursdays, it appears that they're fairly regular in what time they wake up and when they're sitting and when they are moving about. If we look at, say, the weekends, Saturday and Sunday appears to be quite different from the rest of the days of the week. For this week, Saturday and Sunday was highly active compared to Thursday and Friday. For this week, it looks like on Saturday, either the person did not wear their Fitbit or they were quite sedentary and didn't move, which is quite different than any other day of the week. If we look at Sunday, we also see somewhat of an increased physical activity. If we look at the last pair of days in the weekend, Saturday and Sunday, here we also see quite a bit of activity compared to the days of the week. We can also look and see what time does this particular individual usually wake up, or at least when do they put their Fitbit on if they're not sleeping with their Fitbit. So we can see a little bit after 8 a.m. it appears that, or excuse me, a little bit after 7 or 8 a.m. is when this individual wakes up. Now, if we look at when they go to bed, it seems to be around midnight on some nights and as late as 1 or 2 a.m. on some other nights. Now, while this is helpful for exploratory data analysis, it would be nice if we could quantify these changes that we're observing. That way, a numeric score is not as subjective as our visual inspection. We can also perform analysis for a very, very, very large data set if we can write an algorithm to do the analysis for us. So this example here is a specific case of a general problem called change detection and analysis. In one of our previous papers, we addressed this problem with the PAPD approach. This approach is a framework that determines if a significant change exists between two windows of time series data. And in this particular case, the data is step data. And there are 4 main steps to PAPD, which we'll go over each in detail. The first is to take a time series data set and segment it into windows. Those are going to be our windows we want to perform comparisons between. For example, day to day or maybe week to week. Next, once we have our windows, we want to detect changes between the time windows. Now, these changes refer to that numeric score I was talking about earlier. Once we have a numeric score representing the change between two windows, we need some way to interpret that score. So the third step is determine significance of the detected changes. So we'll have to talk a little bit more about what does significant mean. And then the last step is if there is a significant change, then we need to inspect the data to analyze the nature of the significant changes. This diagram here helps explain more about these 4 steps. So imagine you have a Fitbit and it collects physical activity data, which I have an ADM here to visualize it for only 12 days worth of data. Say we segment the data into 2 windows of 6 days each. Call this first window of 6 days window sub I, and the second 6 days window sub j. Then, for step number 2, we can detect a change between these two windows using a change score function that accepts the data in these two windows as arguments. The change score, let's call it CS, is a numeric quantity representing the change between these two windows. For step number 3, we want to conduct a test to see if the detected change is significant. Is CS significant? If it is, then we continue on to step 4 and we inspect the data. If it's not, then we'll go ahead and advance our windows I and J and compute another set of change scores. Let's go through each one of these steps in more detail. So the first one, segment the data. Let's think about the Fitbit example data steps DF, data frame, that we were working with in our previous 2 lessons. It looks like this, where we have 21 columns, each one corresponding to a day, and we have a date-time index corresponding to minutes of a 24-hour day. Here's an example of what this data frame looks like in a more nicely structured table. Let's consider an arbitrary column in this data frame. Let this arbitrary column be called D, and it represents the time series data for one day. There are going to be M values in the time series data D corresponding to the step counts for M intervals. If we have a value called T sub mins to denote the number of minutes per time interval T, then we can figure out what M is. So in our case, we have 1,440 minutes, and there is 1 minute per time interval, so M will be 1,440 for 1,440 intervals. However, this is not always going to be the case. Consider an example where we resample the data hourly. In this case, T-mins is 60 because there are 60 minutes per interval. Then our M, for the number of intervals, will be 1,440 minutes divided by 60 minutes, which gives us 24 intervals. Now, together, all of our N columns, representing N days, is a time series data set called X. And you can think of X as a data frame. Now, if we want to segment our data into windows, then let W be a window of little n days such that W is a subset of X. In terms of X being a data frame, you can think of W as also being a data frame, and it's a slice of X along the date axes. That's our column axes. We can compare windows of data within the time series X. So these windows may represent consecutive times, such as days, weeks, or months, a baseline window with each subsequent window, or overlapping windows. So let's consider 2 windows such that W sub I is a window starting at day number I, and W sub j is a window starting at day number j. Wi and Wj can be formed as subsets of X based on the initial value of I and a parameter offset that determines the initial value of j. So for example, say we want to perform daily comparisons. I would consider this to be a small window comparison. Then our first window might be W sub 1, our offset would be 1, so our second window would be W sub 2. In a medium window, perhaps we're looking at 2 to 5 days, then our first window might be W sub 1, and our second window might be W sub 6. In a large window comparison, say we want to look at a week's worth of data, our first window would be W sub 1, and our second window would be W sub 8. Now, these different window sizes are really going to be dictated by what kind of analysis do you want to perform. If you wanted to do daily comparisons, such as each Monday to each Monday, each Tuesday to each Tuesday, or aggregate day comparisons, where perhaps you're aggregating a month's worth of data into a single day, then you'd set little n to be 1 day. If you wanted to perform a medium window comparison, such as comparing days of the week to other days of the week or weekend to weekend comparisons, then you might set your n to be 2 to 5. 2 for a weekend comparison, 5 for a weekday comparison. If you wanted to perform a large window analysis, such as a weekly, then you might have n set to 7. Or if you wanted it to be monthly, you might have it set to 30 or 31. Now moving on to step number 2, detecting changes. To detect changes, we'll have a change score function f that accepts 2 windows of data and returns a change score cs. These 2 windows, wi and wj, they can be compared in either baseline or sliding window mode. In a baseline comparison, the first window is fixed as the first window in the data set X. It's a reference window and it does not move. For the baseline comparisons, all subsequent windows are going to be compared to this baseline window. So our I is fixed at W sub 1, and our second window, W sub j, is going to advance throughout our data set, starting at offset. Number 2, our second option is a sliding window comparison. In a sliding window comparison, I is initialized to 1 and j is initialized to 1 plus the offset, and the windows slide together, staying separated by a number of days specified by offset. So, for example, comparing a first week to a second week, and then a second week to a third week, and then a third week to a fourth week, and so on and so forth. Using this same example for baseline, we would compare the first week to the second week, the first week to the third week, the first week to the fourth week, and so on and so forth. There are several different options that we can use for our change score function f. There's a short list of algorithms I've included here. If you want to read up on them, please take a look at the links I've included. We're going to take a close look at the virtual classifier in the next 2 lessons. A virtual classifier computes the accuracy of a virtual binary classifier trained with feature vectors for each window. So W sub I would have a feature vector f sub I, and window wj would have a feature vector f sub j. So those feature vectors are going to be used to discriminate between 2 windows using a virtual binary classifier. Here's a table that describes the different aspects of each of these algorithms if you are interested. Moving on to step number 3, test for change significance. Once we have a change score value CS, we want to find out, is the magnitude of CS significantly large? We'll take a close look at how the virtual classifier approach does this. It uses a test of significance to determine if a significant change exists between the 2 windows. We'll code this up in the next 2 lessons. For details on rule-sift texture-based and SWP-CAR significance tests, please take a look at our paper, Sprint et al. 2016. Our last step, change analysis. If a change significance test determines that a change score CS is significant, then we want to determine the source of change. There are several different approaches to capture change across time and individual metrics. A straightforward way is to simply compute the percent change for a feature. You can also use statistical approaches such as 2-sample test or effect size analyses. One thing to keep in mind though when performing repeated statistical tests is you want to account for the multiple testing problem. When we discuss the virtual classifier approach in detail, we'll see that the virtual classifier approach has a built-in way to analyze the source of change using a decision tree model.